All right, so picking up from the middle of that page, was a little worried the video might be getting a little bit too long there. We have another problem here, exploring some of the similar issues between rate law and the mechanism of the reaction, but also introducing a couple new terms here as well. So let's take a look at this one. So we've got nitrogen monoxide is reduced by hydrogen to give nitrogen and water. The reaction is shown here. So again, our reactants are nitrogen oxide, NO, and hydrogen gas. And we're given a possible mechanism for the reaction. So the first step is 2 molecules of NO combining to form an intermediate. That intermediate reacting with hydrogen in the second step to make a different intermediate and a little bit of the product, water, one of the products. And then that intermediate is involved in another additional reaction with a different molecule of hydrogen, and that gets us to the rest of the products for the reaction. So it's a 3-step reaction, and we're asked to evaluate some different aspects of that. So the first question is, what is the molecularity of each step? And in this term, molecularity describes how many molecules of the reactants are involved in a particular step. So it's similar to order. The first step involves 2 molecules of NO colliding. Those are both reactants. So this first step would be considered bimolecular because there are 2 of our reactants colliding. So that would be a bimolecular step. The second step involves a reactive intermediate that was formed as a result of the first step, but it is reacting with one of our reactants. So this step just has one of the reactants involved in the necessary collisions. It would be unimolecular for just one, right? And the same is true of the third step. The other reactive intermediate that was formed in step 2 now is reacting with one of our reactants. So this is also unimolecular in terms of our reactants. So overall, the reaction involves all 4 of the pieces of the reactants. That doesn't mean that it's going to be a 4th order overall reaction. That would depend on where the rate determining step is. What the mechanism is will relate to the rate law. Okay, the second question, what would the rate laws be depending on which step is slow? So 3 different steps, we've got 3 different possibilities here. So let's start with imagining the first step is the slow step. That would mean the other 2 steps are by definition faster, right? So the slow step is the rate determining step. Now, only everything up to and including the rate determining step would show up in the rate law for the reaction. So if the first step is slow, that means the rate law would look like this. The rate of the reaction would equal the rate constant, right? And then the first step involves 2 molecules of NO colliding. So that would mean second order dependence on NO. But everything that happened after that would not show up in the rate law. So this reaction would end up being 0th order in hydrogen if that first step was slow. Now, the next option would be the second step being the slow step. So if the second step is the slow or rate determining step, what would the rate law look like then? Well, the rate of the reaction would equal the rate constant. The first step comes along before we get to the rate determining step, so everything that happens there will appear in the rate law. So we would still be second order in NO, but now getting over this hump, this activation energy in our reaction energy diagram, is going to require a collision that involves hydrogen. So the reaction would take on a first order dependence on hydrogen here if the second step is slow. And then the third possibility is that the third step is the slow step or rate determining step. The first 2 steps are fast. Now if that is the case, 2 NOs, H2 in the second step, and another dependence on H2 in the third step. So in that case, the rate will equal the rate constant. It'll still be second order in NO, but it'll also be second order in hydrogen. So to some extent, right, we could evaluate these mechanisms just by figuring out what the rate law is, by looking at concentration dependence of this particular reaction. Which one matches what we see here could tell us if this is potentially a good mechanism for this reaction or not. Now, the third question, how would the reaction energy diagrams differ. And I'm going to try to do all of these on one reaction energy diagram. We'll see how well that works out. So we'll make a reaction energy diagram here. And again, this is energy on one, reaction progress on the other axis. And let's just set the two fairly even here. Eventually we'll talk about the thermodynamics of that's shown here in some of these reactions. Now, if the first option, where I used my black ink pen, the first step is slow, that means the first step would have a fairly large activation energy, the second step would be fairly small, and the third step would be fairly small. So it might look something like that, right? Once we get by the first step, we're going all the way to the products, no matter what. So the first step is slow, the other two steps would be relatively fast. Okay. The second possibility, where the middle step is slow, in that case you'd start out with a low activation energy. So a fast step would have a low activation energy, the second step would have the higher activation energy, and then the third step would be a fairly small activation energy. So pretty easy to get over the first hump, right? The difficult one is the second hill in the reaction energy diagram. But once we get over the second hill, that last step is really going to happen no matter what, regardless of concentration. And that kind of transition from the first option to the second option would be similar for the third one. If the third step is slow, that means we would have two, actually let me displace this a little bit so it's easy to see. We'd have two fairly fast steps with low activation barriers, followed by a third that has a fairly high barrier. So it'd be pretty easy to do the first two steps of the reaction, right, to make the intermediate necessary to do this third step. Okay, let's see if we can get the last page in here on this particular video. So one last question here in chapter 13, related to the same topic here. We've got a oxygen atom transfer reaction from NO2 to CO. So those are our reactants, NO2 and CO. And that's going to produce nitrogen monoxide and carbon dioxide, so NO and CO2. So basically this oxygen is leaving NO, so we're breaking a bond there, and it's connecting to CO, forming a bond there. What we're told is temperatures below 500, the rate of the reaction, the rate law is rate equals K times concentration of NO. And in this case, right, we've got the rate law. We are going to try to figure out what the mechanism is. So let's look at that rate law. Rate is equal to K times the concentration of NO2. That tells us that the first step in the mechanism only involves NO2. And it also tells us that that has to be the slow step, because where's the carbon monoxide? It must be involved in a step that comes after the slow step. That's the only way it would not appear in the rate law. It's 0th order in carbon monoxide. So that first step has got to be something like this. The NO is breaking apart into NO2 is breaking apart into NO and O. So that's forming one of our products, and it's producing a reactive intermediate, this oxygen atom, and that would be slow. So breaking that bond, it's reasonable that that would be slow. Breaking a bond is generally going to be slower than forming a bond, which is going to be pretty fast. Now the second step would be the carbon monoxide reacts with that intermediate, the oxygen atom, to make the other product, CO2, right? And that's going to be pretty fast. And that would have to be the mechanism. So when we look at a rate law and we see something is 0th order, it tells us a lot about which steps are fast and slow, but also which parts of our reactants might be involved earlier versus later in the steps of a mechanism. Okay, that will wrap up chapter 13.